In this video, I want to really go over some of the key concepts of how to balance a chemical equation through working through a pretty difficult question. If we're just using what we've learned so far, this should be a pretty difficult question. However, at the end of this video, I'm going to show us a shortcut method to how to solve a question like this. So in a question like this, just like any other balancing chemical equations problem, we are going to divide it up and write down the different elements that we have. So I would actually encourage us to try to do this on our own and pause the video here, and then you can check with me. So try to solve this whole problem actually if you can on your own. If you don't feel comfortable with doing that, at least set it up and count how much of each element that we have, and you can check your work with me in just a second. All right, now that we've done that on our own, we will see that we have nitrogen, hydrogen, phosphorus, oxygen, and lead, Pb. Same thing on the other side, nitrogen, hydrogen, phosphorus, oxygen, and lead. All right, we're going to count how many of each that we have. I have 3 nitrogens from here, plus 4 more over here. So I have 7 total nitrogens. Hydrogens, I have 4 times 3. I have 12 nitrogens. Phosphorus, I just have 1 of those. Oxygen, I have 4 plus 3 times 4 is 12. So I have 16 oxygens. And then lead, I just have 1. Moving on to the right side of the equation, I have 2 nitrogens. Hydrogens, I have 4. Phosphorus, I have 4. Oxygen, I have 4 times 4 is 16, plus 3 more. So I have 19 oxygens. And then for lead, I have 3 leads. We'll write that down. Now, if any of that did not make sense to you, please pause this video and go back and watch my video about how to count elements in a compound. I described the different things about multiplying inside and outside the parentheses, and then multiplying all that by the coefficient and stuff. So that video will be very helpful prior to watching the rest of this. All right. Also, if that didn't make sense to you, if we scroll down, I actually have it drawn out for us. I went ahead and color-coded this and then showed us what each of these compounds look like. So you'll see the same numbers written here. Should be the same at least. And I have the elements drawn out so we can double check everything. If we counted different things, we could count nitrogens. I have 1, 2, 3, 4, 5, 6, 7. That's where I get that 7 from, etc. So pause this video here. If there is any of those that I counted out that were confusing to you, feel free to check to make sure that this all makes sense with the drawings that I have. All right, now that we have everything counted out and drawn out for our convenience, we can start solving this problem. We need to look at and see, okay, this is clearly not balanced. We have, in fact, nothing here is balanced, and we got to start from somewhere. Metals and carbon are typically easier ones to start with, and if you're not familiar, lead is a metal. So I think that, and it's just looking here, it looks like we have 3 leads on this side, only 1 on this side. It'd be pretty easy to just put a number here and balance out those leads. So that's where I'm going to start. And so we'll start by figuring out what number goes here in order to get 3 leads on the left side in order to balance that out. So if I put a 3 here, well, now we'll have 3 leads. And it'll change my numbers up. I'll now have 3 leads here. And then it's also, this 3 does not just apply to the lead, it also applies to the nitrogen and oxygen. So I got to recalculate those as well. All right, so 3 leads, and then we also have nitrogens. I have 3 plus 4 times 3 is 15, or sorry, 4 times 3 is 12, 3 plus 12 is 15. So I have 15 nitrogens. For oxygens, let's see, oxygen, I have oxygens, I have 3 times 4 is 12, times 3 is 36, plus 4 is 40. So I have 40 oxygens. Again, we're multiplying, so we have these 4 right here, plus I'm doing 3 times 4 and multiplying all of that by the coefficient. So each one of these molecules has 12 oxygens, and we have 3, or each of these compounds have 12 oxygens, and we have 3 of those compounds. So that'll make sense in just a second. I'll show you what it looks like drawn out. But I have 40 oxygens. All right, that's everything that was impacted by putting that 3 there. Let's go ahead and see what this looks like when it's drawn out. All right, so by drawing everything out, we can count every single one of those elements that we just calculated. So nitrogens, I can count 15 nitrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I can also count what else changed? Lead, that's a pretty easy one. Well, putting this 3 here tells us that we now have 1, 2, 3 leads. And then oxygen, well, I got 40 oxygens. Let's look at that. So 40 oxygens, that's because I have 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, plus 4 more is 40. Let's see, the nitrogen came from there, and then the lead's right there. All right, so we see where all those numbers came from, having it all drawn out now. Doing all of this balanced out the lead, but we still need to balance pretty much everything else. Looking at what else we have here, we're going to see that it's going to be probably easiest to balance phosphate next. All right, so phosphate being the P. All right, and I have 4 phosphates on the right side of the equation, but only 1 on the left side. You don't have to balance phosphate next, but I just think it's the easiest one, so that's just what I'm choosing. There's no correct order in doing this, but there's easier orders and harder orders. So in order to balance out the phosphates, I'm going to have to put a 4 right here. And by putting a 4 right there, I now have 4 phosphates. But this 4 did not only impact the phosphates. It also impacted the nitrogens, the hydrogens, and the oxygens. So I'm going to have to recalculate all of those. Or if you just want to be safe, just recalculate everything on that side of the equation. All right, so the nitrogens, all right, 24 nitrogens. Okay, after nitrogens, we also have to recalculate hydrogens and oxygens, and we already did phosphorus. All right, hydrogens, I have 4 times 3 is 12, times 4 is 12, 24, 36, 48 hydrogens. Okay, and then for oxygens, I have 4 times 4 is 16, plus 3 times 4 is 12, times 3, 12, 24, 36, so 16 plus 36. I have 52 oxygens. All right, I think we recalculated everything we needed to recalculate. Let's look at what we have now after adding that 4 there. So scrolling down, I've got everything drawn out for us. Hopefully this isn't too small to see. But if we want to, we can go through and calculate and count how many nitrogens, hydrogens, phosphoruses, and oxygens we now have afterwards. I have it drawn out, so feel free to pause the video and count for yourself if you don't believe me. But we had only one of these compounds, and by putting the 4 there, we now have 4 of those compounds. 1, 2, 3, 4. And adding those extra compounds added a lot of nitrogens, hydrogens, phosphoruses, and oxygens. All right, these numbers are getting kind of big, and if you're noticing that and you're getting kind of lost and this seems confusing, you're gonna really love the shortcut method, which I'm just about to show you. I've got one more step to solve this question. All right, so the next step of this question, we've got to balance the rest of this. We're gonna notice that lead is balanced and phosphorus is balanced, but everything else is not balanced, and we need to figure out what's to balance next. The oxygen is going to be pretty difficult to balance next because I don't know whether to add a number here or here to balance the oxygen, since it shows up in both of these compounds. So let's skip oxygen. Let's see if we can find an easier one. And nitrogen is only on this in this compound, and hydrogen is also only in this compound. And I would say that between the two, one is not necessarily a lot easier than the other. We have found that we need to put a number right here in order to balance the nitrogens or hydrogens, and we just now need to figure out what number that goes there. So if I need to say what. So let's look at how many nitrogens I have in this compound. I have 1, 2 nitrogens in this compound, and I have 4 hydrogens in this compound. So whatever one you decide to do, I'm going to do nitrogen. So I'm going to say what times 2 equals 24. What times 2 equals 24? Or if I'm doing hydrogen, I would say what times 4 equals 48. And for both of those, the answer is going to be 12. 12 times 2 equals 24. And 12 times 4 is 48. So for either one of those, we're going to see that putting a 12 there is going to help get us our answer. By putting a 12 here, though, we're going to have to recalculate the number of nitrogens, hydrogens, and oxygens. So let's do that. All right, nitrogens, we now have 24 nitrogens. We now have, so 12 times 2 is 24. We now have 12 times 4, 48 hydrogens. And we have 12 times 3 is 36, plus 4 times 4, 16. So I have a total of 52 oxygens. All right, let's see what this looks like with everything drawn out. scroll down, and we get our final answer of 4NH4 3PO4 plus 3PbNO3 yields 1 Pb3 PO4 plus 12 NH4NO3. And later on, we're going to learn about how to use the naming mechanisms we learned to incorporate naming and balancing these chemical compounds. But if you want to double check, you're welcome to pause the video here and double check and see that we have the exact same number. We have this number of oxygens on both sides and this number of hydrogens on both sides. You can count all of the oxygens, all the hydrogens, all of everything else. And we see that with everything drawn out, everything is balanced. Everything is not only balanced, but is also simplified. None of these numbers here, none of these coefficients can be simplified any further. So this is our final answer. And luckily I had some of this written out before solving this, because this is a pretty long problem and you can see that there's a lot going on here. So if you followed along, great, then you're doing fantastic. If you struggle a little bit, not to worry at all, because this was a pretty hard problem. But I'm going to show you a method now that's going to make this problem much, much more simple. So let's go look at how to do that now. All right, as we see, we have the same problem here. Same problem as before, all set up, drawn out. We just need to count. But instead of, when we start setting this up, when we're balancing chemical equations, something that happens in chemical equations or chemical reactions is you have the breaking and forming of bonds. That's kind of a rough definition of what a chemical reaction is. Different atoms that are paired with one another break apart and pair with something else. As we can see, an example of that is lead. It's bound to NO3 at first, and then that breaks apart, and now the lead forms with the PO4. And so we have this breaking of and forming of bonds, and that's why when we're counting things, as we did in the last problem, we counted the individual elements, because we know the individual element, that's pretty much the furthest you can break something down. Unless we're getting into nuclear chemistry, we're not breaking apart individual elements. So that is the smallest units we can get through to in chemical reactions for the most part. But in particular chemical reactions, we might notice that some of the compounds don't get fully broken apart. So, like, instead of having to break everything down into its individual elements, we can say, well, wait, the NH4, for example, the NH4 shows up on both sides of the equation. I'm going to choose a different color. The NH4 shows up on both sides of the equation. It didn't get broken down any further than that. So I could just write down NH4 and just count the number of NH4s, because it didn't get broken down any further than that. So I don't need to simplify it or I don't need to break it down any further than that. Next, I see that phosphate, PO4, is right here, and it didn't get broken down any further than PO4. It remained as PO4. Lead is still there, which is fine. But I do notice that NO3 is on this side of the equation and also on this side of the equation. So notice that some of these compounds didn't get fully broken apart. And particularly, we have a lot of what we've memorized as polyatomic ions. They didn't get broken down any further than that. So when we're counting, we don't need to count them as being broken down any further than that. We can just count we can count the biggest units that we have available. And sometimes that makes things easier, as we'll see in this problem. So when we're counting the number of NH4s, let's look at that. NH4s, I have 3 NH4s on the left side of the equation. I have 1 PO4, 1 PB, and I have 4 NO3s. For NH4, I have 1 NH4, 4 PO4s, 3 PBs, and 1 NO3. So when we're counting these, we count NO3 is all one thing. And so if there were to be multiple NO3s, there would be a parentheses and some sort of number outside the parentheses. Since there's no parentheses, we know that there's only one of that compound. All right, so we counted out what we have, and when we draw it out, we have the same thing as before because it's the same chemical reaction, we're just counting it differently. But we're going to find that counting it differently like this is going to be a lot simpler. So let's move on and see what we mean by that. So once we count it out, we're going to have to start balancing. We can see that by adding a 3 in front of the PB, NO3,4, right here. By adding a 3 there, we now have balanced out the leads. So the order that we're balancing things is actually going to be the same. It doesn't have to be the same, but I liked doing it the same way. We now have 3 PBs. So as we can see, we have 3 of those compounds drawn. That changed the number of leads, and it also changed the number of NO3s. So for NO3s, so we have 3 leads and 3 times 4 NO3s. All right, the next step of this problem, we have to choose something else to balance. We now have lead is now balanced. I'm going to say that phosphate looks like the next easiest one to solve or to balance. So I have 4 phosphates on the right side. I need to figure out what number to put where in order to balance out the phosphates on the left side. If I put a 4 here, I'll now have 4 phosphates, and I'll have 4 times 3, 12 NH4s. All right, a lot fewer calculations because we don't ever have to multiply inside the parentheses times the outside the parentheses times the coefficient. We just multiply coefficient times outside the parentheses. So as you can see, this method's already a lot simpler. We have everything drawn out in case you want to double check things. But if not, we'll move on to what that looks like. So 4 NH3PO4s, we now have all of those drawn out, so you can count everything that we have if you want, which is totally fine. But we're going to have to move on to the next step of balancing this chemical equation. So the next step is going to say, okay, what else needs to be balanced? Let's see, PO4s are balanced, PB is balanced, but NH4 and NO3 is not balanced. So choose one of those and balance that next. It doesn't matter which one you choose, they're both just as easy to balance. So I'm going to say NH4, let's try to balance that next. I have 12 on the left side. I need to figure out where to add a number in order to get 12 NH4s on the right side. This has nothing to do with NH4s, so I know that I'm going to add my number right here. And I need to figure out what number do I need to put here in order to get 12 NH4s. And the answer is going to be, if I put a 12 there, then I'll have 12 NH4s. So putting a 12 there, it's going to give us 12 NH4s and 12 NO3s. So by doing that, we have now balanced the left side and the right side of the equation. And if we want to look at what our final answer looks like drawn out, here's what it is for us. Hopefully this isn't too small to see. But if you want to pause the video and count anything that didn't make sense to you, you're welcome to do so. But everything's drawn out and balanced and in its simplest terms. So again, the point of, you don't ever have to leave these compounds as, you don't have to leave them like this. You're always welcome to do it the original way of breaking them apart into their individual elements. But this is just a faster more simple way to solve these. So it's just kind of a shortcut. Feel free to use it. All right, now to practice what we just learned, let's go ahead and try to solve this problem using that same method that we just learned about. So pause the video, try to solve it on your own, and then you can double check your work with my answer here. All right, now that we're done solving on our own, let's go ahead and count what we have. I have chromium, Cr. Looks like I have nitrite, NO2. I have ammonium, NH4. And I have sulfate, SO4. I'm going to write the same thing on the other side. Chromium, nitrite, ammonium, and SO4. SO4. All right, we're going to count how many of each one we have. I have 1 chromium on the left side. I have 2 nitrates. I have 2 ammoniums. And I have 1 SO4, sulfate. On the right side, I have 1 chromium, 1 sulfate, and 1 ammonium, and 1 NO2. So I need to figure out where I need to add a number in order to balance this out. Well, noticing that chromium and sulfate are both already balanced, I know that I'm going to be focusing on nitrite or ammonium, either one. So nitrite or ammonium, doesn't matter. I'll just do nitrite. Nitrite, I have 2 on the left side, but I only have 1 on the right side. So I need to figure out what number needs to be added right here in order to balance out the nitrite. If I add a 2 here, then I will now have 2 nitrites. It'll apply to all of this. This 2, if we did the individual elements, it would apply to all of the individual elements. But since we're solving this as grouping things together, this 2 will apply to this group of elements, and it will also apply to this group of elements. All right, so this tells us that we're going to have 2 nitrites and 2 ammoniums. And then when we look at what we have over here and over here, looks like everything is balanced for us. So nice work on that. All right, so hopefully this is helpful. It was just kind of this. In this lesson, we kind of went through some kind of an advanced problem if we're solving the traditional way, but a shortcut method to make hard problems like that a lot easier. So when you notice these polyatomic ions, and specifically when you notice a group of elements that are the same on both sides of an equation, no need to separate them any further than that. Just keep them grouped together, and it'll make solving these a little bit easier. Feel free to use this method as you wish. You're welcome to always use the prior method of breaking apart everything into their individual elements. Hopefully this is helpful. Tune into the next video. Bye.